This video is on wavefronts, rays, reflection, and refraction. Question 1. Define wavefront. A wavefront is a surface which travels with the wave. Sometimes the wavefront represents the crests of the wave. Question 2. Define ray. A ray tells us the direction a wave travels. A ray always points perpendicular to the wavefront. Rays must have arrows to tell us the direction the wave travels. Question 3. Draw 3 wavefronts and 6 rays after a small rock falls vertically and hits water. So imagine a rock hitting water, and then these circles, the very center of the circle is where the rock hit the water. So these circles are called wave fronts. They represent the crest of the wave. And these lines with arrows are the rays. Question 4. Draw 2 wavefronts and 8 rays after a long thin rod falls horizontally and hits water. So you could see that this is like a big stick here in the middle. It falls and it hits the water. The wavefronts look like the 2 red ovals or curved surface. And remember, the rays are always perpendicular to the surface. So I drew 8 lines or 8 curves that are supposed to be 90 degrees from the wave front. Question 5. Define superposition. If 2 or more identical waves meet at the same point at the same time, then the displacements of the wave will add up. So important, do not confuse the term displacement with amplitude. Question 6. Draw a before, during, and after image of 2 pulses on a rope traveling in opposite directions which go through constructive interference. Okay, so look at the first image on the top. Before interference, 2 waves with positive displacement move towards each other. During interference, the displacements of the waves add up. And then after this interference, it's like the 2 waves never interfered. The 2 waves will keep their same wave properties, like displacement, amplitude, wavelength, and period frequency. So you can see on the top image there's a wave going to the right, and then at the bottom image it continues to go to the right like nothing happened. And on the top image there's a wave going to the left, and on the bottom image there's the same wave going to the left. And after it interfered, after the 2 waves interfered with each other, once they passed each other, it's like they had their original properties. Question 7. Draw a before, during, and after image of 2 pulses on a rope traveling in opposite directions which go through destructive interference. Okay. So before, you have 2 waves traveling in opposite directions, like they're coming towards each other. One has positive displacement, one has negative displacement. During interference, the displacement of the 2 waves add up. So you have positive displacement plus negative displacement, same magnitude, opposite directions, they cancel. So you get 0 displacement. After interference, after the 2 waves interfere, it's like the 2 waves never interfered. The 2 waves still keep their same wave properties. So the wave with positive displacement moving to the right continues to move to the right, The wave with negative displacement moving to the left continues moving to the left like they were never communicating with each other. Draw a before and after image of a single pulse wave on a string striking and being reflected from a vertical pole with a fixed end. So, fixed means not moving. So before, this wave travels to the right, and then after, it travels to the left. It's reflected, but it's also inverted. So the wave is inverted if it is reflected off a fixed end. There is a phase change of pi, or 180 degrees. Question 9. Draw a before and after image of a single pulse wave on a string striking and being reflected from a vertical pole with a free or loose end. So if this little ring here on the right, which is connected to the rope, is free, it can move up and down. So when this wave travels to the right and hits this ring, the ring goes up and down, and the wave continues to travel to the left. So the wave is not inverted if it is reflected off a loose end. There is no phase change. Question 10. What is the equation, units, and meaning of index of refraction n? What is a range of values for the refractive index of an object? What is a refractive index for a vacuum? So little n equals c over v. C is the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. V is speed of light in a specific medium, like the speed of light in glass, the speed of light in air, the speed of light through water with some things in it. Little n is the index of refraction. It has no units. The index of refraction n is a ratio of the speed of light in a vacuum to the speed of light in a specific medium. And n is always greater than or equal to 1. For a vacuum, n is equal to 1. Question 11. The speed of light in a vacuum is 3 times 10 to the 8th meters per second, while the speed of light in a diamond is 1.24 times 10 to the 8 meters per second. What is the index of refraction of diamond? N equals c over v. Question 12. The index of refraction of light in water is 1.33. What is the speed of light in water? So we know n equals c over v, solve for v. Question 13. Light, which has a wavelength of 450 nanometers, is moving through carbon tetrachloride with a speed of 2.056 times 10 to the 8 meters per second. What is the index of refraction of carbon tetrachloride? So the wavelength didn't matter. So that was extra unnecessary information. Part B, what is the frequency of this light wave as it passes through the carbon tetrachloride? So V equals lambda F. We were given lambda, we solved for V. I apologize, we were given lambda and we were also given V. Part C, what would be the corresponding wavelength of this light wave in air? So if light passes from one medium to another medium, then the frequency does not change. So it's going to be traveling from carbon tetrachloride to air. So we could say F1 equals F2. So V1 over lambda 1 equals V2 over lambda 2. And just solve for lambda air. Question 14. Light, which has a wavelength of 625 nanometers in air, enters flint glass. The index of refraction of flint glass is approximately 1.63. Part A, what is the speed of light in flint glass? So n equals c over v, and let's solve for v. Part B, what will be the wavelength of this light within the flint glass? If light passes from one medium to another, then the frequency does not change. So now we have this equation, f1 equals f2. Take this equation, solve for f. So v1 over lambda 1 equals v2 over lambda 2. And just solve for lambda 2. Part C, what is the frequency of this light within the flint glass? So V equals lambda F. If light passes from one medium to another, then the frequency does not change. So they want us to find the frequency. The frequency is the same. 4.8 times 10 to the 14. Part D, what is the frequency of this light in air? Well, the solution for C and D is the same. Frequency in air equals frequency in glass. So we've already found frequency in glass. Question 15, define reflection and draw a labeled figure. Reflection is when a wave bounces off a surface. So theta is measured 90 degrees from the surface, not parallel from the surface. So this vertical bold black line is the surface. The line perpendicular is called the normal. Okay, it's the normal line. And where you see this number 1, that's theta 1, and where you see this number 2, that's theta 2. So we have an incoming wave that hits the surface, and then there's an outgoing wave. Where 1 and 2 is theta in and theta out. So I define reflection is when a wave bounces off a surface and I draw a labeled figure. Question 16, state the equation for the law of reflection. The law of reflection states that theta in equals theta out, where the angle is measured perpendicular to the surface. So here we could see theta in equals theta out pretty much. Question 17, define refraction and draw a labeled figure. Do not confuse refraction with rarefaction. Refraction is when a wave travels from one medium or volume to another medium or volume. A popular example of refraction is a bending of a spoon or straw when in a half full glass of water. So play with this simulation. Go on this website and you could play with this simulation. As you could see, you could change on the bottom the index of refraction of the block. You could go from 1 to 2.5. So this light purple is air, this dark purple is like glass. It's like a medium. And you could see this angle of the red coming into the normal is equal to the angle when it's out from the normal. So play with this simulation. As you could see, they have an index of refraction of medium 1, an index of refraction in medium 2. And the angle in medium 1 is 45 degrees, and the angle in medium 2 is 26.95 degrees. Okay. Question 18. State the equation for refraction, Snell's law. So, also draw an image, I guess. Snell's law states that when a wave is traveling from one medium to another medium, n1 sine theta 1 equals n2 sine theta 2. We know n is equal to c over v, so put c over v on both sides. Divide both sides by c, and now we have this relationship. So remember, theta 1 and theta 2 are both measured from the normal, not the surface. And f1 equals f2. So imagine you have something that looks like this. Medium 1 is on the left, medium 2 is on the right. If a wave is traveling through air, bam, in medium 1, and it hits medium 2, and now it travels through glass on the right side, you see you're bending toward the normal. Because you go from fast to slow, you bend towards the normal here. Okay. So, question 19. Draw a detailed image of a ray traveling from a fast medium to a slow medium. So this is the same image. We have a vertical line in the middle. On the left-hand side, we're traveling through like a fast medium, like air. And on the right side, we have a medium that's slower than air, like glass. And rays traveling from a fast medium to a slow medium bend towards the medium. I'm sorry, bend towards the normal. The normal is a dotted line. Question 20. Draw a detailed image of a ray traveling from a slow medium to a fast medium. So you can see we switched it. Medium 1 on the left is slow, like glass. Medium 2 on the right is fast, like air. And you could see if we go from a slow medium to a fast medium, we bend away from the normal. Question 21. Define dispersion and draw a labeled figure. Dispersion is when light travels into a prism and leaves as a rainbow. So there are many beautiful images about dispersion if you just go to a search engine's image section. So we have light coming in, white light, and what we get coming out is Roy G. Biv. Remember, Roy G. Biv is red, orange, yellow, green, blue, indigo, violet. And the meaning of indigo violet is purple. Question 22. A wave, which has a wavelength of 1.4 meters and a wave speed of 4.8 meters per second, enters a second medium where the wavelength is reduced to 0.9 meters. What is a wave speed in the second medium? So we know V equals lambda f. When we go from one medium to another medium, f is the same. So just take this top equation and solve for f. V1 over lambda 1 equals V2 over lambda 2. Question 23. A wave moving with a speed of 38 centimeters per second and having a wavelength of 4.5 centimeters strikes an interface at an angle of 57 degrees relative to the normal. In the second medium, the speed of the wave is reduced to 24 meters per second. So part A, what will be the angle of the wave in the second medium? So we have this equation here. We're given V1 and V2. And we're given theta 1. So we solve for theta 2. And know how to do sine inverse on the calculator. Okay. Part B. What will be the wavelength of the second medium? So V equals lambda f, f1 equals f2. So just solve for f in this first equation. V1 over lambda 1 equals V2 over lambda 2. And solve for lambda 2. Part C, what will be the frequency of this wave in the first medium? So V equals lambda f, solve for f. Part D, what will be the frequency of this wave in the second medium? Well, they're both equal to each other. F1 equals F2. Memorize that property. Part E, which medium has a higher index of refraction? So N equals C over V, the second medium has a higher index of refraction. Question 24. A wave moving with a speed of 1.25 meters per second strikes an interface at an incident angle of 82 degrees. After passing through the interface, the angle shifts to 55 degrees and the wavelength becomes 5.6 centimeters. Part A, what will be the speed of this wave in the second medium? So they want the speed, so let's just use this equation here. Solve for V2. Make sure your calculator is in degrees. Part B, what would be the wavelength in the first medium? V equals lambda f, f1 equals f2. Use this first equation to solve for f. V1 over lambda 1 equals V2 over lambda 2. Solve for lambda. Part C, what will be the frequency in the second medium? Well, we know f1 equals f2. So just use the equation V equals lambda f and we could solve for f. Question 25. A light ray which has a wavelength of 580 nanometers strikes a horizontal interface going from air into flint glass. Given that the angle between the incident light ray and the normal to the interface is 47 degrees. The index of refraction of flint glass is approximately 1.63. So part A, what would be the corresponding angle in the flint glass? So n1 sine theta 1 equals n2 sine theta 2. We know little n in air is about 1. And we were given that little n in flint glass, the index of refraction is 1.63. We were given theta 1, so we could solve for theta 2. Make sure your calculator is in degree mode. Part B, what will be the wavelength of this light within the flint glass? V equals lambda f. So V1 equals lambda 1 f1, divide that by V2 equals lambda 2 f2. We know f1 equals f2. We could solve for lambda 2. Part C, what would be the frequency of this light within the flint glass? So V equals lambda f, solve for f. Part D, some of the light reflects at the interface. What would be the angle between the reflected light ray and the normal to the surface? Well, we have the law of reflection, theta n equals theta out. Question 26, a light beam traveling through glycerol, which has an index of refraction of 1.48, enters an interface at an angle of 67 degrees relative to the normal to the surface. The corresponding angle in the second medium is measured to be 50.5 degrees. What is the index of refraction of the second medium? So just solve for N2. Question 27. A light wave moving through an unknown medium encounters an interface at an angle of 52 degrees and then refracts to an angle of 45.2 degrees into lucite, which has an index of refraction of 1.5. What is the index of refraction of the first medium? So solve for N2. I apologize, this should be N1 here. N1, because they gave us N2 and theta 2, and they gave us N1. Question 28. Define total internal reflection and critical angle. So total internal reflection tells us that during refraction, if theta n becomes too large, then there is a critical angle, theta critical, in which the wave will not be refracted, only reflected. This only occurs if the wave travels from a high medium to a low medium. So let's use Snell's law here. For the critical angle, theta 2 equals 90 degrees. And sine of 90 is 1. So now we have this equation. You see what happened? Sine of theta 2 went away. So play with this total internal reflection simulation here. Okay. We have theta coming in at, we have theta coming in going up, because critical angle only happens from going to a high medium to a low medium. So on the bottom we have water, on the top we have air. As we increase theta, we have reflection, the thin line going back, and refraction. Here we're increasing theta, so we have reflection and we have refraction. Here we have now reached the critical angle. We have reflection but no refraction, nothing coming out of the other side. And here we've gone beyond the critical angle. Once again, you only get reflection, no refraction. So to repeat, when theta is small, we have reflection and refraction. When theta is bigger, we have reflection and also refraction. There is a theta where we only get reflection. And then if we increase theta more, we only get reflection once again. Question 29. A light beam is moving from flint glass into water. So that's high medium to low medium. What is the critical angle between these two mediums? The index of refraction of flint glass is 1.63, while the index of refraction of water is 1.33. Okay. So we have this equation here. Solve for theta. Question 30. Determine the critical angle between the following two media. We got diamond and water. So we have this equation. We know theta 2 equals 90 degrees for critical angle. Okay. Recall that the light must travel from a high medium to a low medium. Make sure your calculator is in degrees. And we're solving for theta 1. Part B, what's the index of refraction between alcohol and lucite? So N1 has to be 1.5, because that's the higher index of refraction. And 2 has to be 1.36, because that's the lower one. And lucite is N1. N1 is in the numerator, and sine theta 1 is in the denominator. Finally, what's the critical angle between hot air and room temperature? So you could see they're almost the same. Little n goes from 1.02 and 1. So n equals 1.02 has a higher index of refraction. We always go from high density to low density. So hot air is going to be N1. And solve for theta 1.